कम्प्युटर साइन्स र इन्फर्मेसन टेक्नोलोजीका प्रोफेसनल कोर्सहरूको लागि सब्स्क्राइब गर्नुहोस् टेक-शास्त्र युट्युब च्यानल। Hello students, welcome to Tech-Sastra. In this video you will learn about Euler's method. Euler's method is the numerical approach to solve differential equation or the initial value problem. First of all, I will derive the formula for Euler's method. In second part, I will solve one problem using Euler's method, and in the third part I will write C program. Okay, so I will do these three things in this video, so the video may be a little bit lengthy, but I will cover everything you need to know about the Euler's method. But before starting these things, let me make you the problem more clear. We may have a given differential equation of the form dy by dx is equals to function of xy, and we have also given the boundary condition, that is y at x naught is equals to y naught. Suppose the question may ask us to find at xn what is yn. That is the problem. Or if you follow this notation, then the question may be asking y at xn equals to what. Okay, if we take this differential equation over here, the solution of this differential equation is a function, say y is equals to fx. Then we can plot that function in the graph. If we take any independent variable x naught, the corresponding value is given to be y naught. For x naught, it will be y naught, right? But we have to find out functional value corresponding to xn. But here the function is fx and we are unknown about this function. Okay, that is the main problem. So that we have to follow the numerical method. If we know the given function, then we will follow the calculus. But here we know only the initial condition and the given differential equation. Based on these things, we have to approximate what will be the functional value corresponding to xn. So I hope the problem is clear to you. We can solve this problem simply by using Euler's method. So let's derive the formula that we are going to use in Euler's method. Derivation. Let's imagine the given differential equation is just the same one. Okay, and its solution is y equals to fx. This is the solution for the given differential equation. And we have the initial condition, that is at x naught the function becomes y naught. And we have to decide at xn how much is yn. So here what we can do is, we can divide this interval x0 and xn into sub-intervals. So here may be x1 and here may be x2 and so on. Let's say the functional value corresponding to x1 is y1. Similarly, the functional value corresponding to x2 is y2. Then one thing you can clearly see over here is the Taylor series expansion. If we take only one interval, then also we can use the Taylor series, but the value approximated will be suffering from large error. So to overcome that, we can decide to divide the given interval into more and more smaller intervals of equal size. Let's say the interval size is h. Let's say we are defining n intervals. This is first interval, second interval, and this is the nth interval. Then from Taylor series, we can write y1 equals to y0 plus h y naught dash plus h square by 2 factorial y naught double dash plus h cube by 3 factorial y naught triple dash, and so on. But if we take the intervals extremely small, then for very small value of h, we can neglect the higher powers of h. Then the Taylor series gives us y1 equals to y naught plus h y dash naught. Similarly, for another interval, we will get y2 equals to y1 plus h y1 dash. For another interval, we will get y3 equals to y2 plus h y2 dash, and so on, right? So if we generalize this, we can say yn will be equals to yn minus 1 plus h y dash n minus 1. But if you look at the given form of the ordinary differential equation, y dash is dy by dx, which is function of xy. So y dash will be equals to f of xy. Yn equals to yn minus 1 plus h f of x comma y, but at which point? N minus 1 point, right? So this way I can derive the formula for Euler's method. So it is basically the Taylor series method where the higher power of h is neglected. So we can use this formula to solve the given differential equation or the initial value problem by using Euler's method. This formula can also be derived in another way. Here we derived this formula by using the Taylor series method. But we can derive the same formula by geometric method also. Here the differential equation is definitely of the form dy by dx is equals to function of xy, y at x naught is equals to y naught. If we consider fx is the solution for the given differential equation again, and if we take the given initial condition, so we have to find the yn. Okay, again let's imagine we draw a number of subintervals corresponding to the points x1, x2 and so on, right? If you draw a tangent at this particular point, then if you look at this triangle over here, let's say this angle is theta. Alright, now taking the slope, that is tan theta is equals to this perpendicular divided by base. Perpendicular means this height, which is nearly equal to y1 minus y naught, right? So y1 minus y naught divided by this is x1 minus x naught. So this gives what? This is the slope, so we can write dy by dx is equals to y1 minus y naught divided by this is h. From the question we can write dy by dx as f of xy, y1 minus y naught by h, but this is at the point x naught y naught. Okay, this is also at x naught y naught. Then it gives us y1 equals to y naught plus h f x naught y naught, right? This is for the first interval. Similarly, if we take the second interval, we will get y2 equals to y1 plus h f x1 comma y1, right? So if we generalize these expressions, the final expression comes out to be yn equals to yn minus 1 plus h f xn minus 1 comma yn minus 1. So this is our formula for Euler's method. So let's go ahead and solve a new problem. The question says solve the given initial value problem using Euler's method. To find y1, take h is equals to 0.2 and the function is y dash equals to x plus y, y0 equals to 0. We have to solve it by using Euler's method. So first of all, let's write the given things. Y dash, or we can write dy by dx equals to, it is also called f of xy equals to x plus y, right? Another is x not given, y of x naught equals to y naught. So x naught is 0, y naught is equals to also 0. Now point at which we have to find the solution, that is xn is equals to 1, and question has given h equals to 0.2, the interval size is this much. Then we can write this formula, that is n equals to xn minus x naught by h. This will give us the n, that means the number of intervals, that is 1 minus 0 divided by 0.2 equals to 5. Okay, so to solve this problem, draw something like this. If this is the solution, y equals to fx for the given differential equation, we have at x naught, that is x naught equals to 0. So this must be the origin, but no problem. So here is y naught, and we will draw how many intervals? Altogether 5 intervals, and ultimately we will end to xn. The functional value will be y of xn, we can say, or yn. Here xn means what? 1, and yn is how much we have to find out. Sometimes we may have given this h, sometimes we may have given this n. If h is given, we can apply this formula to find the value of n. But if n is given, we can decide h ourselves. We can take any value of h, but if we want more accurate value, we have to choose as small as possible. From Euler's formula, we have yn equals to yn minus 1 plus hf xn minus 1 comma yn minus 1. Then for I equals to 1, x will be 0.2, because initially x naught was 0. We have to go for x1, x2, x3 and so on. Each time the x will be incremented by 0.2, because h is 0.2 as given by the question. Next will be 0.4, next x will be 0.6, next x will be 0.8, and next x will be 1.0. Okay, so how many iterations we have to go? Definitely we have to go for 5 iterations. Basically here is n. So when n is 1, x is 0.2, then the formula becomes y1 equals to y naught plus h of x naught y naught. This will be equals to y naught is 0 given by the question, yes, and then plus h is 0.2 into f of x naught y naught will be how much? F of x naught y naught will be x naught plus y naught. So I'll write here x naught plus y naught, x naught plus y naught, and this will be 0.02 times x naught is 0 plus y naught is 0. So y1 will be 0, right? Similarly, for n equals to 2, if we take n is 2, then x, here is x1, so x2 will be 0.4, and the formula gives us y2 equals to, applying this formula, y1 plus hf x1 y1. y1 will be 0 from the previous solution, plus h is 0.2 always. Function of x1 y1 is x1 plus y1, and this will be 0 plus 0.2 times x1 plus y1. x1 is how much? 0.2. y1 is 0. So it gives us 0.2. It becomes 0.04. Okay. Similarly, for n equals to 3, x3 will be 0.6, and y3 we can find y2 plus hf x2 comma y2. So y4 can be found and y5 can be found, and this will be our final solution. Now let's go ahead and write the C program for Euler's method.